Modern municipal infrastructure relies on a massive interconnected grid. Millions of individual environmental sensors, surveillance cameras, and streetlights require constant two-way communication to function effectively. Down at the street level, beneath a standard signal head, a physical traffic sensor registers a passing car. It generates a single pulse of data, a vehicle count packet bound for the traffic management center. To cross the network, this packet requires a unique, globally reachable return address. It needs an exact digital location, so the data center knows precisely which intersection just reported in. When you have millions of physical assets spread across a grid, real-time management collapses if the central servers cannot directly identify and route commands back to every single individual device. For decades, the Internet relied on Internet Protocol version 4. IPv4 used a 32-bit address space, providing a hard mathematical ceiling of about 4.3 billion unique addresses. In the 1980s, that supply seemed inexhaustible, but the rapid proliferation of always-on internet connections, laptops, and mobile PDAs quickly drained the available global pool. To delay a total collapse, engineers deployed Network Address Translation, or NAT. This acts as a stopgap, funneling multiple local devices through a single shared public IP address. It hides an entire local network behind one external-facing IP. Any incoming message has to hit the router, which then forces the return data to be analyzed, translated, and sorted to find the correct internal destination. That translation takes time and processing overhead. If you rely on split-second timing to route emergency vehicles or adjust traffic flow, a shared bottleneck parsing data for 1 million overlapping sensors is a liability. To bypass that bottleneck entirely, this traffic sensor operates on a different standard, IPv6. This protocol expands the address space from 32 bits to 128 bits. Instead of a short decimal sequence, an IPv6 address uses 8 groups of 16 bits, written in hexadecimal characters, 0 through 9 and letters A through F. By dropping the leading zeros within these blocks, the address becomes significantly shorter and easier to parse. Managing these long addresses manually across a grid of this size would require meticulous tracking, with high risks of human error and address conflicts. Instead, the network relies on automated assignment. When our traffic sensor powers on, a protocol called DHCP-v6 automatically leases it a unique IPv6 address, configuring its connection parameters without manual intervention. This automated process scales effortlessly. Devices can join or leave the physical grid at any moment, and the system maintains perfect addressing hygiene without an administrator typing a single hex character. The specific address assigned to our packet's destination is Unicast. It designates a strict one-to-one conversation between the traffic sensor and the traffic management center. This contrasts with a multicast address, which identifies a group of devices. A single multicast command can hit one address and simultaneously instruct an entire city block of streetlights to dim their output. What IPv6 completely removes from its architecture is the legacy broadcast function, which used to force every device on a local network to listen to messages sent to all hosts. Stripping out broadcast traffic ensures that millions of small, low-power sensors are only woken up for data directly concerning them. It preserves battery life and reduces processor overhead across the entire metropolitan grid. With its destination set, our packet leaves the physical housing of the sensor and hits the boundary of its local intersection network. This image explains the default gateway, the specific router that acts as the exit door connecting a local network to outside networks. Without this gateway, our packet would be trapped communicating only with other devices physically wired at that specific intersection. As it moves out onto the wider grid, the packet relies on the User Datagram Protocol, or UDP, to carry its payload. Unlike TCP, which demands back-and-forth acknowledgements to ensure perfect delivery, UDP is connectionless. It ignores air checking to prioritize pure speed, which is ideal for a simple, fleeting vehicle count tech. At the network layer, the city's core infrastructure utilizes the Open Shortest Path First Protocol, or OSPF, to navigate the physical topology. Operating like a real-time GPS, OSPF analyzes the link states between routers. As the packet shifts through the fiber optic grid, The protocol continuously calculates the most efficient, shortest path to the data center. The combination of UDP's lightweight transport and OSPF's dynamic pathfinding guarantees the vehicle count reaches the analytics engine before the physical traffic conditions can shift. The packet arrives at the traffic management center. The servers immediately ingest the data, authenticating the unique IPv6 source address of the street-level sensor. The software processes the lightweight UDP payload, logging the vehicle count and calculating that the congestion at that intersection requires an immediate signal timing adjustment. The server instantly dispatches a response, a Unicast command routed completely unhindered back to the sensor's exact 128-bit address. This clean, NAT-free bidirectional exchange directly impacts a physical world. The intersection light turns green, and the physical traffic bottleneck clears. Zooming out, you see billions of independent connections pulsing across the city grid, simultaneously managing water flow, electrical distribution, and transit networks. IPv6 restores the original end-to-end principle of network design. It reestablishes an architecture where any two nodes, regardless of location or hardware, can communicate directly without middlemen or translation layers. The true value of a 128-bit hexadecimal structure is its scale. It provides a mathematical canvas so vast that every manufactured object on Earth could be assigned multiple addresses without denting the supply. It guarantees the physical and digital infrastructure will never run out of space. The foundational network is secure, built to support whatever volume of automated hardware the future demands.